All right, so in this discussion, we'll go through some methods that you can use in PowerWorld Simulator to analyze historic geomagnetic disturbance events. And a good chunk of this presentation will be material that we've presented before using some data that we get from the NOAA Space Weather Prediction Center website. There will be a couple of new elements added. I wanted to show where we have a repository of events from the NOAA SWPC that are just in our format, in our PowerWorld Simulator binary format for GMD events that are just ready to be loaded directly into PowerWorld Simulator. And the other thing that we've kind of introduced relatively recently in PowerWorld Simulator is the ability to load a set of time points from the GMD tool into the Timestep simulation tool for doing power flow analysis. So that's a little bit of a new element here. The rest of it will be some review of things that we've covered and things that we've posted in our knowledge base before, but hopefully it's useful and it kind of shows how all of it ties together. That's kind of my goal for this session here. So I'll talk a little bit first about non-uniform modeling and historic event files and where they can be obtained and where you can also get near real-time data from the NOAA SWPC. Let me change this option on the pointer here so that it's always visible. Okay, so one of the things that NOAA has been working on, and actually some other efforts that were funded by the National Science Foundation and some other groups to get the data together is this effort to put together empirical data based on the actual response, measured empirical response of the Earth. So EarthScope was a project that the NSF funded from 2003 to 2018. There's also the U.S. magnetotelluric array, and then the successor to that is the empirical magnetotelluric transfer functions, or EMTF, which is the data hosted at the NOAA Space Weather Prediction Center. So this aims to gather the actual response of the Earth resistivity to a changing magnetic field in the atmosphere based on measurements that are taken in a grid. And what NOAA's trying, what they're measuring directly is the magnetic field response in the atmosphere during an event. And then they're running it through these transfer functions, either 3D transfer functions or 1D transfer functions that are kind of the legacy function, which I'll talk about in just a moment, in order to get a picture of the surface electric fields in a geospatial and time varying manner. So the Earth models are basically describe how that transfer function works. For the 3D Earth models, there's still some data gaps. Most notably, it's really just the continental U.S. and it's missing some parts of Southeast Texas. But we can read this data in or the data based on the 1D Earth model transfer functions as well in our time varying E-field calculation mode, which I'll show in just a moment. This is from the NOAA SWPC website at this address right here. And this is the coverage for the 3D model. So if I switch over to the website right now, I'll show you a little bit more about that. Okay, so here's the link from the slide right there. And it's got two tabs right here, one that's based on the 1D transfer function. The advantages of this is it's got more coverage. So it goes up to 60 degrees north latitude in Canada and throughout the continental United States. So that's going to cover, of course, most of the footprint for North American power flow cases with maybe just some gaps in northern Mexico. But it's based on, again, just the 1D transfer functions. These are the ones that are described in the NERC TPL 7 documents. And again, it's just based on resistivity measured looking straight down into layers of the Earth from the surface. So this other tab right here shows, and this is current information right here on the website. I don't know if it's refreshed, but I'll hit refresh here. So yeah, it's based on 8 p.m. UTC, which is basically right now, or just a little bit delayed from real time. And this is the this is again the 1D model. Here's the 3D model. So again, this is based on a different transfer function that's gathered from empirical data, and it covers most of the continental United States. So the examples that we look at later in this discussion will make use of these models, but from NOAA, you could download either one. So lower on the website right here, they've got some tabs that describe different aspects of these different models. The 1D model or the 3D model explains a little bit about them. And then the data tab right here has some links to where you can actually download the near real-time data. So if you follow one of these, either for the 1D model or for the 3D model, it'll take you to a page where it's got a rolling set of GeoJSON files. That's a format. It's a text-based format. It's rather verbose. So the examples that we look at later, we basically condense that data into a binary format that PowerWorld Simulator can read. But if you have a need to get data based on what's happening right now, then you can go here. It is a little bit, if you're doing it manually, it's a little bit of a labor-intensive process, because you would have to like download each one of these files, and each one represents a time point, I think, on one minute intervals. And if you click on any one of them, then you can actually look at the data. But this is the GeoJSON format. It is very verbose, but it's got the electric field calculation, northward and eastward components of the vector, of the electric field vector, at each geographic point in the grid that's covered by the data set. So that's one source. What we've done is we've worked with NOAA to get this historical data for some significant events that have happened over the last 20 years or so. And that's described in the slides here. So anyway, here's the 3D model. Here's a screenshot from the 1D model. And again, those are based on the 1D conductivity or Earth conductivity regions from the US Geological Survey and Natural Resources Canada. And again, these are the based on the transfer functions that are used in the NERC TPL 7 standard. So we have a repository on our website where, again, we've worked with NOAA SWPC to get a set of files that cover these historic events, actually going back more than 20 years, back to the March 1989 storm. And then most of the rest of these are for the last 25 years or so, Bastille Day, Halloween. The rest of the slides, I'm going to use this as an example, but if you're interested in these files, you can get them from our website. And here's the link right here in the knowledge base. If you follow that link on that slide, it's got each one of these events right here. And if you click on those, you can download a zip file. It's a large file because it contains the entire event, which, you know, on 1 minute resolution and half-degree geographic resolution, it spans 2 or 3 days. So there's a lot of data points in there, but it's just one file. It's not a large collection of GeoJSON files. It's one file in our binary format, which we'll look at in just a little bit. So those are all available there. And so, yeah, in PowerWorld Simulator, you can open the GIC analysis form. and I'll go over to PowerWorld Simulator right now. So I have a case open. You can run this example in any case, and then also after this presentation is over, I will make the files that I use available on our website for download if you're interested in going through that. But if I open the GIC dialog, this is on the add-ons ribbon right here. The way the events are initially loaded in is you would make use of the time varying electric field inputs calculation mode. And this screen's grown quite a bit over the last few years with the development that we've done in PowerWorld Simulator. But to load the data in, you start with the open file button right here, and then you go pick out the event file or files that you want. There's actually a way to open multiple files inside the same directory of the same type. But what I did was I grabbed this file that you can download from our website for the Halloween Storm event right here. It's already loaded, so I'll hit cancel. But actually, before I do that, I'll show down here the different file formats that we can load. So the JSON format can be loaded. NOAA previously used a different text file format with the DAT extension, and I think they've moved away from that, so that's probably obsolete. But if you have old data laying around in that format, that can be read as well. Normally, this historic data like this would be in the B3D file format or the GeoJSON format. So, and if you have multiple files, like if you're loading a bunch of GeoJSON files, there's options to grab multiple files that are in the same directory, basically, and load them all together. But the B3D format, the binary format, supports multiple time points in there. So when I loaded that file, it loads in on 60-second resolution, 5,040 data points. So that goes out 302,000 seconds, or kind of the better part of 2.5 days, I think, worth of data. So basically going from midnight on, this might be kind of hard to see here, midnight on October 30th, out to, and this is UTC time right here, out to almost noon on the 2nd of November. So it's got that time period. And there's some ways just directly within this dialog where you can do some sorting to see, like, for example, what's the highest electric field that occurs anywhere geographically within that time period. And if you do that, you can see what time it corresponds to. It would be at 12:40 p.m. on Halloween. And then you can browse over here the data for that time point on the geographic grid. And so this data has 3,432 points on the grid, basically spanning latitude and longitude for CONUS. It doesn't have to be like a rectangular grid. It can be just any arbitrary set of latitude and longitude points. But the NOAA data is basically on a 1/2 degree resolution. So if we wanted to sort, for example, by the field magnitude here, we can see that the 7.6 volts per kilometer that we see as the maximum across all time and all geography, we can identify the time at which it occurs and then the geography at which it occurs. So, but of course, the interesting thing is to be able to simulate this data against the power system. So we'll take a look next at some ways you can do that. But basically, yeah, we loaded the data in on the case, and this is the name of the file. And once it's loaded, another thing that you really need to be able to do in order to use other tools in PowerWorld Simulator, like transient stability and the power flow, is to create a time varying series for it. And if this box is checked, it'll do it all in one step. There are ways kind of beyond the scope of my talk today where you could load in multiple events and superimpose them on one another, in which case you might want to do all of that loading first and then set up everything at the end. And there's ways to do that too. Again, kind of beyond the scope here, but if I switch the calculation mode to time varying series voltage inputs, then what we'll see is the result of the path integration on all of the transmission lines for all of the time points in the data set. So this is the units up here on the time points are in seconds. So the start of the event has a 0 reference, and then every 60 seconds, there's another set of data. And then the result is basically just a DC input voltage that goes on each transmission line. So that path integration is performed, and it's that data that's then directly used in PowerWorld Simulator to do the GIC calculations. And then it can also be used in the nonlinear power flow or the transient stability tool if the box is checked up here. So the next thing we'll take a look at is how you can get a bunch of summary data really quickly using the transient stability tool. And I say transient stability tool because that's just the interface in PowerWorld Simulator that's used to process the data. In my example, I'm not actually going to do a dynamic simulation. It really doesn't make very much sense for data on this granularity of once every 60-second sample. And generally, the dynamics of a GMD event are slow enough that the transient stability isn't really salient. There are cases where, like for example, with high altitude EMP, like nuclear detonations in the atmosphere, in the late time domain, so you typically on the order of seconds out to several minutes, there's much faster rise times and dynamics there. And to do that type of analysis, we actually do dynamic simulations with the transient stability tool. Here, we're not going to do that. But there's a way with our transient stability tool that you can set. I'll kind of skip ahead on these slides, but they're included here for reference. This is kind of what I showed in the application earlier, how you can kind of do the sorting to just get some feel for the magnitude of the event and where the peak of the event is and so forth. But what we might want to do again is run that through our transient stability tool to get some summary and to get some plots of what's happening over time, to be able to visualize that on a plot. So that's what we'll do next. In transient stability, there is an option in the tool specifically for geomagnetic induced current effects, to just run those through the tool without doing a network solution. And by network solution, we mean the dynamic solution, the numerical integration that's necessary to do a normal transient stability analysis. We can ignore that and just process the GIC data through, and then use all the tools within our transient stability tool, like result storage and graphing, in order to create some plots. So that's what we'll do. I'll come back over here to simulator, and I'll close this. And then on add-ons, I'll go to transient stability. And here it is. And you can name the event. This is just, like other transient stability analysis, except for we're probably not going to have, if you're familiar with using the tool, you would normally have like some contingencies down here, some events that would be happening that would perturb the dynamics of the system that we'd be interested in analyzing. Here, we're not going to do that. We're just going to basically run the GIC, the time varying GIC through the tool. And I'm using a time step of 60 seconds because that's the resolution of my event data that I got from NOAA. so that the start time and the end time match the time reference, the time offset in that event also. And the option that you would want to check, because you wouldn't want to actually try to do a dynamic simulation with parameters like this, is under options, you would go to the power system model and then check this right here. So we're just going to calculate GIC with no network solution. And as we'll see, for lots of data for 5,000 plus different time points, it's fairly quick. If I just come back up here to the simulation and then click run transient stability, it'll march through it in about a minute or so. So while it's doing that, I should have mentioned at the beginning too, if you have any questions, feel free to put them in the chat and I will take a look at them at the end. But anyway, this is the setup that we did. And we've got some in the files here. I've already got some plots defined, so we'll see those at the end. But some of the things that you might want to do just to get kind of a high level feel for the event and where the points of greatest stress on the system might be is to look at the total reactive power losses for the entire case. Or maybe if you're just concerned with a certain control area, if you are interested in your utility or maybe the ISO or the RTO that you're part of, you could have area or super area definitions that span that area of interest, and you could just make a plot for those, for example. But in this example, I'm going to just take a look at system-wide reactive power losses and also the highest geomagnetic current, effective current that occurs in any transformer. That's a field for the case information object, which in transient stability refers to the entire case. So if you had other things that were of interest, of course, like if there's a particular transformer that you're concerned about, you could run traces for that in the plotting tool in transient stability and then take a look at the results at the end. So this is what the trace looks like. I'm going to come back over to simulate. Oh, it's done right now. So like I mentioned, it just takes about a minute to run through all those time points, and that's kind of the advantage of that. So you can see that the data that was that kind of defines the storm, it starts off kind of quietly. There's not much going on here. The red trace is the total reactive power losses across the entire case. And as I mentioned, you could do plots for maybe just an area of interest or something smaller than the entire case. The blue trace is looking at what's the worst GIC current in any transformer. It doesn't identify in the trace what that transformer is, but you can mouse over. Of course, this is just applies to any plot that you do with the transient stability tool. If you mouse over the plot, it'll give you some statistics and it'll tell you what the maximum value is and where it occurs. But we can see that the kind of the interesting part of the event falls. There's a little bit right here, but the real peak is kind of like in here. So we might, just kind of zoom in on that, and we might conclude that we want to do a deeper analysis maybe at these time points to see what happens during the nonlinear power flow solution. Again, if it were an EMP event on a smaller time scale, you might want to actually do a dynamic simulation as well, which again is not really salient for what we're looking at here. So we're just using this information, again, to get a quick overview and decide what time periods we might want to look at a little closer. So one way you could do that is you could figure out, which time points have the highest reactive power losses, or maybe the highest GIC flows through transformers of interest or through any transformer in the system using these traces. And you could come back to the GIC tool and just zero in on those time points that you wanted to do a solution for. So for example, I could come back here and then I could set the offset time right here. Like for example, if I just wanted to go to like where's the highest field, I could set that offset to 132,000 seconds right here. And I could do the GIC calculation. And then I could also do the nonlinear power flow. And then maybe look at the changes in voltage. I could use the difference flow tool to set a reference case. I could solve the power flow, the nonlinear power flow at this point. And then just, if I have just a few points that I want to analyze, that could be a very, very effective way to do it. So I can see, the message log here in simulator will tell you that it's including, it'll give you a message to say, we're including the effects of the transformer reactive power losses from the GIC on the power flow. So it'll put a bunch of reactive power mismatches at buses that are impacted by that, and then solve the power flow. And so you might get different voltages. I could come, like for example, in my contouring tool and look at changes in voltage for that time and apply them on the contour. Oops, I didn't switch. I forgot to switch to my difference mode right here. So I'll do that real quick. And then, yeah, it looks like we don't have a whole lot in. Recalculate it. Yeah, but there might be some other time points where it is significant. If we look at the time where the worst case reactive power flow loss was from the transient stability. Oh, and I lost my graph here. But if I go back to my plot, so I could identify this time point right here with the maximum losses, and that's at 201,300. So I could come back and analyze that time point too. So anyway, you get the idea. You could go, if there's just a handful of time points, you could just manually go through them one at a time. But what if we wanted to do a power flow solution for a range of times, like during this peak of the event, or even the entire event? If we had time for that, of course, it could take a long time to do the processing with power flow solution, 5,000 different power flow solutions. But if we really needed that data, we could solve all of them, or we could just solve a certain range of them from a start to a finish. And ways that we can do that, the slides have some summaries of things that we just looked at. So there's a zoom in on some particular time range of times on the graph. But if we want to look at the nonlinear power flow solutions, again, we could just look at the power flow solutions for those time periods that look like they're the worst from the traces. But if we wanted to look at many time points, we could use automation using scripting. And there's a script commands, of course, that do the calculation of the GIC with the power flow solution if you want, and then save the results out. You can use our SimAuto automation server to drive that, and then save the results out to text files or to a SQL server or other database like that. Or you can use the Timestep simulation tool. And so that's what we've kind of introduced more recently with PowerWorld Simulator 24. And there's tools to do that. So if I go over to that tool, if you're not familiar with the Timestep simulation tool, it is included with the base package. So everybody who has simulator has the Timestep simulation tool. You can go on the tools ribbon right here and then go to Timestep simulation. And I've got a bunch of data points that I already loaded into this file just in the interest of time and making it not having to wait on it for the presentation. But if you needed to insert them, you can go up here and click insert time points if you had a blank grid right there. And there's a mode now where you can insert them based on the range of times that are present in the data in the GIC tool. So basically what we just loaded from the NOAA SWPC data, we could tell it to use that. A lot of these options down here they're not grayed out, but effectively you don't need to enter start dates or number of time points if you've selected this option. They mostly apply to this first option for manual entry. But with that, you can then just, if you click OK, it'll put in the whole range of time points that you need. And the result is what you see here. So again, it starts at this date and time and ends down here. And then what we can do is we can just do a PowerFlow solution. If you needed to do the whole thing, you could tell it to run. What I did for illustration here was I just solved a range of time points. This data has the skip field set to yes, and this Timestep data will be in the set of files that I make available afterwards. But it skipped those and it ran the ones that are just kind of in the heart of the event where the E fields were the highest. So it's got some summary data right here. And then we also have some results that are stored for the entire case. So the reactive power losses right here. So this would basically be the same trace that you get out of the transient stability tool if you wanted to plot it. The plotting tools that we have with the Timestep simulation are not nearly as sophisticated as the ones over in transient stability, which is why I would suggest running, if you've got a large event and you don't know what the most significant time points or range of times is, run it through the transient stability first. But you also can, using the case information toolbar up here, you can go to columns and plot columns, and it'll show. I didn't do the solution for all of the data, so you'd have to kind of zoom in. But basically, you see the same trace as what's in the middle of the one that we got from transient stability right there. And then what we did here is we also saved for transformers what the GIC currents were. And again, there's not really a great plotting tool that's native right here. But this is also something that you could calculate, or you could store rather, with the transient stability data too. So if you needed detailed plots for certain transformers, you could do that there as well. What this tool again is useful for, though, is it'll do the nonlinear power flow solution. So we could go to a range of points if we wanted to see, like, for example, what the system looked like at the, I think it was already solved over here from manual. That's 1240. I come back over here. Again, these are like all in the slides, but like the time of maximum power flow losses was at 7:55 a.m. on November 1st. So again, that corresponded to 201,300 seconds from the reference. But if I wanted to find that time point in the Timestep simulation, I can just go to that by scrolling down to it. You could right click on the time and then choose solve this selected time point, and then bring those results up in the GUI and on the one line diagram. So here's my voltage contour. Again, it's not showing the difference right now, but if I applied the difference mode to it, I can see how voltages dropped during that time period of maximum losses. And again, if I wanted to look at the data, if I've got it stored here, I can look here on my results under buses. I've got the per unit voltage for a whole bunch of buses that were stored after the run. And what you might want to do here is just use the tool to send all the results to Excel, because again, our plotting tools that are native to the Timestep simulation tool are not very strong. You can select multiple columns at a time and then plot them, but it's a little bit clumsier. But yeah, I can do that at least. I can zoom in and I can see how this voltage is varying. But you can also send it out to Excel and just do some analysis there as well. Like look at the highest and lowest voltages gate currents for transformers, or voltages for buses, or losses on the case. So yeah, you can really choose to store, using the Timestep simulation tool, the result storage. Again, we've got some training topics on the website that go into kind of the mechanics of doing this more, and you'll be able to see it if you download the files that we provide afterwards. But basically, there's a way where you can come in here and just tell it what results to store for which objects. So it doesn't by default store everything, because that would be very, very memory intensive. But you know, once you get the results, then you can browse them here. You can send them out. But again, if you need to look at lots of different power flow solutions or over a range of time, it can be a helpful tool. So here's a trace of voltage at a particular bus. We can see here, we could compare that to our reliability criteria, and we might conclude or have some assessment, I guess, of what the severity of this particular historic event would have been based on the modeling, of course. So here's a trace of transformer GIC, and this corresponds, this 31 amps that you see at this time point right here at 9:30 a.m. On November 1st corresponds to the same value that we saw here in the transient stability plot, where we just looked at the worst case transformer at each given time point. The 31 amps right there corresponds to what we see on that trace. So different ways that you can look at it, but again, the transient stability tool is great for quickly processing the data just based on the GIC calculation. The Timestep tool can be useful for doing nonlinear power flow solutions. And if it's an event like nuclear EMP, where the dynamics are faster and kind of fall into the transient stability realm, you can then use the transient stability tool to actually do the dynamic simulation as well. So anyway, this is the trace that I showed, after solving that time point in the Timestep simulation. There's also tools in the Timestep simulation where you can have it save a bunch of graphic files out for each time step. So there's lots of things in there that you can do if you needed to be able to visualize data over time.